So we're looking at compound inequalities now. And there are two types of compound inequalities. There are the and compound inequalities, and there are the or compound inequalities. And they look very different. An and compound inequality, algebraically speaking, would look something like this. And this would be read, you read from the middle out. You would say x is greater than or equal to 2 and less than or equal to 5. I'll say that again. You read from the middle out, and this says x is greater than or equal to 2 and it says x is greater than 2 and less than 5. Now, or inequalities, on the other hand, are going to look like two separate inequalities with the word or in the middle, so they're not really that challenging. And it might look like this. X is greater than or equal to 2, or x is less than 1. Now, they look very different when you graph them as well. If I were to sketch a graph of the first compound inequality, I would want my boundaries at 2 and 5. I would put open holes on each of them because there's no or equal to here. And my solution set consists of all the x's that are between 2 and 5. So I would simply shade looking like this. And again, this would be read, x is less than 5 and greater than 2, or x is greater than 2 and less than 5. It's an and inequality. This one here, when I go to graph it, I want my boundaries at 1 and 2. For 1, since it's strictly less than, I'm putting an open hole on it. And for 2, it's greater than or equal to, so I'm going to close that hole. Again, the reason I do that is that 2 is part of the solution set, because 2 is indeed greater than or equal to 2. Now, if I want to start shading, all the x's less than 1 exist to the left of 1, and all the x's greater than or equal to 2 exist either on 2 or to its right. So, in the red over here, I have an and inequality, and in the blue over here, I have an or compound inequality. Now, let's look at solving some of these algebraically. The first one I have written here is -5. I'm sorry, I shouldn't read it that way. I should read it as 3x plus 4 is less than 19 and greater than -5. I'll say that again. I should read this from the middle out. 3x plus 4 is less than 19 and greater than -5. Now, my ultimate goal is still to get x alone. So two things are happening to x. Somebody multiplied 3 and somebody else added 4. The easiest thing to undo is to subtract 4. Instead of subtracting 4 from both sides of an equation or an inequality, we actually have to subtract 4 from 3 pieces here. I subtract it from the -5, I subtract it from the 3x plus 4, and from the 19. -5 minus 4 is -9. That will be less than 3x, which is less than 19 minus 4 is what, 15? Okay, we're halfway home. I still want to get x by itself, so I need to divide everything by 3. Now, I'm not dividing by a negative here, so I don't need to flip any inequalities. But when I do this, the middle is x, less than 5, and greater than -3. This is the algebraic solution to that compound inequality. If I wanted to graph it, and I'm kind of running out of space, but I'll do it anyway. If I wanted to graph it, I would create a number line indicating or representing the x-axis. I'd want to know where 0 is. -3 would be there. 5, for argument's sake, would be there. Again, I don't care if you have all the hash marks indicating -2, -1, 1, 2, 3, 4, and 5. That just seems like it takes up a lot of time we don't need to waste. I'd have an open hole on the -3, an open hole on the +5, and my shading would go between those two boundaries, representing all the x's that are both less than 5 and greater than -3. I'm going to erase that now just to give me a little bit more space. My next compound inequality, it says 3x plus 8 is greater than 17, or 2x plus 5 is less than or equal to 7. This you just handle as two separate inequalities. You end up graphing them on the same number line at the end. I'm going to subtract 8 from both sides of this inequality, giving me 3x is greater than 17 minus 8 is what, 9? Divide by 3, divide by 3, and I get x is greater than 3. Over here, I write or. When I subtract 5 from both sides, I end up with 2x is less than or equal to 2. Divide by 2, divide by 2. leaving me with x is less than or equal to 1. So when I go ahead and graph this on a number line, this or compound inequality, I want to have 1 as a boundary. I want to have 3 as a boundary. There's an open hole on 3 and a closed hole on 1. Again, the closed hole on 1 is because it's a greater than or equal to. And the open hole on 3 is because there is no or equal to. It's just strictly greater than 3. All the numbers less than 1 are going to exist to the left of it. So I shade to the left and put an arrow. The values of x that are greater than 3 will exist to the right of 3. So I shade in that direction and I put an arrow there. And this right here is the geometric representation of that algebraic solution to our original compound inequality. Now, you will end up getting questions where you're simply given the graph of a compound inequality and asked to represent it algebraically. This first one in black. My first clue is that all the shading is between the two boundary points, and that's going to be an and compound inequality. So I'm going to say x is less than or equal to 5. I said less than or equal to because the 5 is shaded in. And at the same time, x's are greater than negative 3. This is an algebraic solution to that geometric representation. It shouldn't surprise you then that the next one here, written in blue, is an or compound inequality. And I'm going to write it as two different inequalities with the word or between it, so it's not really that big a surprise. X is less than negative 1, because I had an open hole on the negative 1, or x is greater than or equal to 1/5. And again, this algebraic solution represents that geometric representation of these compound inequalities.